All right, so this is for Thursday the 5th of November, and it's Pkt2 class number 12. I'm going to share that. Share that screen. All right, today's going to be a good one, I think. It was good in class. I mean, I was having fun. I don't know how much fun they were having, but we're getting into some of the meat of the whole, history of physics. We jump up to Newton. Galileo's good, and I was going to today do a whole thing on Galileo. I postponed that because we got into what we were doing, or I did, and I didn't feel like it was needed. The Galileo thing can go anywhere, really. I may do it tomorrow, being Friday and all, but I don't know. So this is where we left off last time, and it's same as third hour. Now, I have since gone in with third hour today, and I think I asked you guys to go through and do all the triangles, do all the, add to. We had just done a couple of them on Wednesday, and so we pretty carefully went through and checked these to see if what we're doing is, remember, we're looking at the slopes, so we're looking at the velocities. Nice feel. We're looking at the velocities of the ball as it rolls, steel ball as it rolls down that tube along the different points, and the tube is like 9 meters long. So there's 9 holes. This graph was made for a steeper incline. So the time, 7 seconds was all it ever took. Well, now we took 8.5 seconds, but it's okay. If we just go to 7 seconds, that's going to give us some really pretty good data from third hour and you guys. All right, so here's how I did the Stegosaurus tail. These are all, by the way, these are all secant slopes. So remember, a secant touches a curve at 2 places, or back from geometry, this will come up today, back from geometry class, remember, if you have a circle, then a secant is going to hit that in more than one place, right? It'll hit it in 2 places. So these are secant lines. But what about a tangent? How many places does a tangent line hit a curve, or in this case, a circle? What do you say? You think tangent, this is critical to today's discussion. So when you think tangent, how many places does a tangent hit a curve at?
3, maybe.
We got to come back around. These are lines, right? Tangent line, secant line. So tangents are defined that they hit a curve in one place. So a tangent kisses the curve, is what I would say. Kisses it, so kisses a circle. So the only way to me to draw a line to kiss that circle, I want to kiss it. Okay. One way to draw a line is to make it hit it in one point, right? So it turns out, so the green is a tangent. And the orange are secants. Turns out this is pretty huge in the history of physics. So that's a secant and that's a secant. So tangent lines, like I draw on the tangent line, now it only hits the circle. It could be a curve though, but in geometry, the reason I do that way is because that's how you learned it. You might have forgot that day, but you learned it out on a circle. Heck, go on it. Okay. Fine art of hugging the little ruler there. There you go. So those are tangent lines and secant lines. Okay, that's going to come into play here in a little bit. So these, because these blue triangles, because the hypotenuses of the blue triangles hit the curve, these lines right here hit the curve at two places for each one of these, you know. Those are called secant lines. Those are secant slopes. Well, secant slopes are average slopes. They're average velocities. All right. So what we have to do next is to come down here and in this table right here to list those secant slopes. Okay, easy enough. So because we made it nice and easy. We made that it divide by the, you know, it's 1, and so the base is always 1 second. So that makes it easy to find the slopes. Okay, so first one from 0 to 1 is 0.3 meters per second is what we got. You might have 0.2 there. It's probably a better answer, but we did 0.3. 0.3. These are all meters per second. Notice these are all V bars. They're all average velocities. The next one is 0.4. Okay, now we're thinking, remember, we're thinking like Isaac Newton. Galileo couldn't do this because Descartes had not invented the graph yet. So, this came up in the third hour today. So Galileo is mostly, I read this in one of his books once, one of the books about him, and I was shocked. Galileo did not hardly use algebra. Galileo used mostly geometry because who invented algebra? It's not one person. What group of people invented algebra? The answer is the Persians. So the Persians, and there was a guy, and I kid you not, you know, in algebra you do algorithms. Oh, it's an algorithm, right? Algorithm. That was a Persian. So they invented, they were like there was a guy named Tusi from the Middle East. Middle East was the hotbed of science and math in the 1400s. While Europe's going through these Middle Ages, Persia is just exploding with science and math. And then, of course, theocracies come in and wipe it out. One of the main enemies of a theocracy is science. Sort of like our current administration, a war on science. Well, this has happened throughout history. So Persia, though, before that war on science by the theocracies, led. Well, Galileo didn't have benefit of algebra, much algebra, because it hadn't really gotten to Italy. But by the time Newton comes along, Newton has two huge advantages over Galileo. He has the Cartesian coordinates. He has graphs. This is 1680s now. Galileo was doing his stuff in early 1610, 1620, in that range. Now Newton comes along, we're looking 1680s, 1690s, and he has the benefit of graphs because of the Frenchman, Descartes. He has the benefit of geometry, Greeks, as did Galileo. He has the benefit of algebra because algebra had gotten to England by then. Okay. So Newton's got more to work with than Galileo did. Anyway, back to this. So 0.4 meters per second for between 1 and 2. Between 2 and 3, we said it's 0.6, 0.6. And then I'm just reading this off, 0.9. And then we had 1.1, 1.4, and 1.7. 1.1, 1.4, 1.7. So those are our slopes. Now these are secant slopes, which I said means average slopes, but when you plot anything average, average is always flat. Average slopes are always flat because you're saying that for all these numbers, I'm taking the average, right? So the averages don't change, at least within intervals. Okay, so we need to plot these averages, these average velocities versus, and they're interval velocities in a sense. I mean, yes, they are average velocities, but they're average with a small delta, a small change in time. Only 1 second as opposed to 7 seconds. Okay, so this graph down here, this next graph beside the table there, I guess I'll do that in purple. Well, let's get our times down. So the axes doesn't change. Time doesn't change. 1, 2, and this is a graph down below too, and it won't change for that either. So let's do them both at once. 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. What? I got off a little bit. That's weird. Oh well, it doesn't matter. That one, as you'll find out. And then this one, this vertical axis now, we've got to make that velocity. And it looks like my range is 0 to 1.7. And I want to use as much as I can. So I'll blow this up a little bit. So if we go 0, 0.3, 0.6, 0.9, 1.5, and 1.8. Okay, so this is meters per second. And this is V bar. All right. So V bar, like if I do average force, that's flat. If I do average acceleration, that's flat. If I do average velocity, that's flat. But I'm taking it along different points. So I'm going to have a series of flat functions. All right. So maybe go blue. Okay. That's the hardest thing I have to think about. What color? So 0 to 1, we go 0, and then this is flat, and open circle at the end. We're used to doing this kind of stuff. Only this time, like in the previous worksheets, we would do flat, 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 flat. But here, the velocity is changing with one. I mean, it's not a piece. It's a step function, but we're trying to get a feel for how velocity is changing, how average velocities are changing over time. Okay, more about that. So 0.4 is next. And now you do this along with me. I'm gonna thicken that up a bit. Okay. 0.6. 9. 0.9. 1.1. 1.4. Okay. And finally 1.7. So you can look at this and say, well, looks like we're quantifying it at least. We're quantifying that ball speeding up. But now we're, and 0, 0, of course, we know that's a point. At 0 time, there was 0 velocity, so that's a dot. A dot, not a flat line. Okay, well, here it starts to get a little weirder. So now I'll give you a minute, and I want to plot. It really helps to have a little graph paper handy. Sarah, one of my students, went to Office Depot, and by the way, if you're listening to this recording, your notebooks are probably on my front porch if you're virtual. You need to come by and get those unless you just don't want them anymore. But you can do it on paper or loose paper if you want. But anyway, you need some graph paper. But Sarah went to Office Depot and she got a really good notebook, and it's full of graph paper, but it's very light. You know, the ink's very light, so it's not like in your face. And it's thin, kind of thin pages, unfortunately, but it's only like $4, $4.50, I think. And so that's really a good deal. It's something you need. It's always good because we're doing all kinds of drawings and graphs all the time, and it's good to have graph paper. Okay, so this is the graph I want you to do, and this is going to be a mathematical graph, not from data, but I guess we can go ahead and, since in general this is X versus Y, but let's keep the theme going here. So this is X, let's just do X in meters versus T in seconds, but this is theoretical, okay? I want this graph to be perfect. So let's say that the function we are plotting here is simply X equals T squared, keeping the theme of Galileo. Remember, Galileo said that then the ball rolls down the ramp, and he rolled hundreds of balls down hundreds of ramps at different angles. And he said that every time he did it, that the X was always proportional to T squared. So let's say, or X equals KT squared. Let's say that our proportionality constant's 1. Okay. So X equals T squared. We're going to plot that. X equals T squared. Now you can kind of sketch it, but this actually requires that it be more accurate than a sketch. I apologize, I didn't warn you ahead of time. I didn't realize I'd be doing this. I came up with this first hour today. And by the time third hour came around, it was pretty good. Now, I always feel sorry for first hour. But they get to watch the sausage being made, you know. I mean, it's not so bad. Well, you keep working and I'll plot our points. So if X equals 1, if X equals 0, then T equals 0. Okay, that's easy enough. If X is 1, T is 1. Okay. So 1 over 1 up, which is not very much. X is 2, T is 2, X is 4. Oh, yeah, right? And then if X is 3, T is 3, X is 9. 4 is 16. 16. 5 is 25. 636. 749. Ball rolling down, a theoretical ball rolling down a perfect ramp. All right, so it's a function. Let me go ahead and connect it up. You keep catching up. Trying to do better. There's a reason for my OCD here. I mean, it needs to be pretty close to perfect, as you'll see. No, it's not terrible. I'm going to erase my dots now. You keep working on yours, getting yours looking better. Erase these. They just get in my way. Now, as I was telling the kids, I am trying to get you once again to think like the greatest thinkers ever in history. And one of those top 5 has got to be Isaac Newton. So I asked him, I was throwing out names and seeing where they ranked them. Isaac Newton is definitely top 5. There's no argument. Galileo, top 10. Stephen Hawking, top 20, maybe. Marie Curie, probably top 20. Einstein, you got to put Einstein top 5. I mean, come on. And I'm naming physicists. I mean, there's amazing other philosophers, Socrates and all these people, and great writers and poets and philosophers. I mean, there's, but definitely, my point is, I'm trying to get you to think like the great thinkers. And since I happen to be teaching physics, that's the best I can do for you. If I get you to think like them, if you think like Einstein, or you think like Newton for 10 minutes, that's pretty good. Do that 10 minutes a day. Here we go. So first thing we're going to do is I asked the question again, what's the slope of this curve? We know it's a silly question because it has multiple slopes. The slopes are increasing. But if I get an overall slope, okay, we'll do the overall average, and that's just going from beginning to end. So let's do that first. And this is our secant line. It hits that curve in 2 places. For secant, tangent, it doesn't have to be a circle, it can be a curve. So I'm drawing a secant line. Now the slope of the secant, equals V bar, equals my average velocity, all right? But Newton was not happy with an average velocity. He wanted instantaneousness. He wanted instantaneous velocity. This was the obsession that allowed him to invent calculus. Newton, by the way, did not call it calculus. Newton called it Fluxions. If something's in a state of flux, what's going on? I'll wait. Something's in a state of flux.
Is it changing?
Changing, right? So things in a state of flux are changing. So it makes sense that I thought it was a great word. I prefer that to calculus. Calculus is a building up. Like you develop calculus in your teeth. So the dental assistant has to scrape it off, right? It's harder. That's a calculus. And I understand that for describing calculus, because when you're doing integrals, you are building things up, finding areas, right, underneath curves like we did with the finger dance. That's calculus. But what Newton first came about studying was change. And so Fluxions, to me, is a great word, but it's out of the lexicon now. It's kind of been lost. But it was Gottfried Leibniz, a German, who developed calculus at the same time, or a couple of years after Isaac Newton. And Isaac Newton accused him of plagiarism, and basically then set out to ruin. I think Newton must have been a narcissist as well, because he could not take a joke. He was petty, but he was a genius. But he then set out to destroy Leibniz, and he did. Leibniz was an amazing German, great philosopher. He invented the calculator. He invented a calculator way before Babbage ever did. Charles Babbage. Anyway, so like Klingensmith in her room has a book, and I have this book somewhere. It's at home, but it's called The Calculus Wars, and it's not the great book. It's okay though, but it's the story of Newton versus Leibniz. Okay, so Newton is not interested in averages. He wants instantaneous change. He wants the flux, the Fluxion. So he wants the instantaneous change in the speed of that ball. How fast is that ball going at any given instant? So when I'm taking instantaneous change, I'm talking tangent. I'm saying to kiss the curve. So let's try and draw some tangent lines. It really helps to have colored pencils. So now, very carefully, I'm going to kiss that curve. Bum, 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 kiss it. Okay, there's one up there. Go one down here. I don't want to go. I want to hit one place. Okay, kiss it. Okay, so you're kissing the curve here, and these green are tangent lines. Tangent lines. And a tangent line, okay, so the tangent slopes, the slopes of these green lines, tangent slopes represent instantaneous velocity. Tangent slopes are instantaneous velocity. Now, what's the symbol for instantaneous velocity? The symbol for average velocity is V bar. What's the symbol for instantaneous velocity? Anybody want to hazard a guess? You know what it is? V. Just plain V. So when I say plain old V, I mean instantaneous velocity. If I put a bar above it, I am humiliating that V. This right here is humiliation for the velocity, to put a bar on top of it, branding it. So you are an inferior velocity, you are average. But I want instantaneous, and so does Newton. Okay, so, but remember, Newton has not invented calculus yet. He's not invented Fluxions yet. He's still messing around. And someone asked, wasn't this year, it was last year, someone asked, well, so are you saying that Newton rolled the balls down the ramp a bunch? No. No. Newton used Galileo's data. It happens a lot. Like Kepler did not look at the stars. Kepler, quote, stole Tycho's data, right? Tycho's the one that looked at the stars. Yeah. And then Galileo used Kepler's data to help him understand a lot about conic sections and about astronomy later on. And then Newton used Galileo's data. So, you know, there's a progression. Progression from Galileo to, well, Galileo, I may have told you this, but Newton was born the year Galileo died. And one author posited that, well, the world can only have one genius at a time. So we keep doing this. Now here's the trick. I want to find a place along this blue curve where its slope is parallel to the orange slope. What time do you think? And just take your ruler. You need a ruler in here. You need a clear ruler, a ruler you can see through, not a piece of paper. Something that's clear, transparent. I'll pick them up for $1 at Walmart. But if I go to 3, look, if I go to 3 seconds and I kiss that curve at 3 seconds, okay, kissing the curve, at 3 seconds. Come on, man. Yeah. Okay, let's do it. Is that green line that I just did parallel to the pink, parallel to the orange line? Are they railroad tracks? No. Let's go to 4 seconds. Kiss that curve. Next year I'll make a sheet, but a huge. It's kind of how I write sheets. One year I think, hey, let's try this. And then the next year I write a sheet, and then the next year I make the sheet better. And that's how the program grows. Now that one is closer. It's hard to tell on my green lines, but that one, this one right here is a little closer, but still not like when they're parallel, they got to be parallel forever, right? Parallel lines never touch, infinitely long. So where do you think? So 3 was too shallow, 4 was too steep. So where do you think the point should be? What the Goldilocks, right? What's the just right point? Anybody want to hazard a guess?
3.5.
3.5. Okay, very good. 3.5. There's a zoom point for you. I don't think you guys are going to need zoom points. So at 3.5, if you line up your railroad tracks right there, and then draw. I'm going to thicken this in. Let me thicken this up. There's the green ticket. That point, at that point, that mid-time. So that the mid-time at 3.5. At 3.5 seconds. Tangent slope equals secant slope. So this is the crucial time. This is where, even if you don't do calculus, even if you haven't, even we're not doing calculus, right? We do graphical calculus a lot. But even without calculus, we can still fool the data so that at that point, we have calculus for an instant. We have, and calculus means, when I say calculus, I mean tangent. When I say tangent, I mean instantaneous. Okay? So at that instant, at the mid-time, these things are true. This is worth writing down. There's an essay question on this on the next test, I promise you that. At the mid-time, the slope of the, write this better. The tangent slope write it better. The secant slope. The secant slope equals the tangent slope. Okay? At the midtime. Oh, whoa. This is if we're dealing with the parabola. If parabolic. This okay. So if parabolic, which means second order. When we talked about this, that means second order. Hey, Nancy Lee, I'm doing a class up here. Is that just a present for Jamie? My neighbor. All right, so that means second order. Doesn't work, by the way, does not work for third order. Students will try and do it in third order. You can't. This little magic trick only works for parabolas. So at the midtime, secant slope equals tangent slope. That means that V bar equals V. That means that average equals instantaneous. And that means that algebra equals calculus. So one brief shining moment. That happens. Okay? Now we're going to take advantage of that. So how can we take advantage of that? Boom. We're getting close. We're not that much further to go. We're going to take advantage of that right here on this trio. On this graph. So back on this V versus T graph right here. I can collapse each step now down to a point. I can collapse each step down to a point. So I'm going to put a dot at the center of each step. Now that dot, 0, 0, I'm going to keep that. But now I'm turning my steps into dots. Dot, dot. Okay, now you do the same thing. We used to erase the steps, but I like to keep the steps there so we can see more of the history of it. Okay. So when we could do that because of that little trick, because their average equals instantaneous. Okay. Now I can do a best fit line through those points. And I'm not going to hit all of them, but I'll get as close as I can. Best fit line. Let me thicken that up a little bit. Thicker, thicker, thicker. Best fit, boom, there we go. Oh yeah, that's good. See, it's pretty good data. This is real data. I did not make this data up. We collected this in third hour. We rolled a ball on the ramp on our courtyard at Norman High School, and look what happened. It is a really good best fit line. This is showing me the effects of gravity as something rolls down a hill. Now, we came at this from a handicap point of view. I don't like to say handicap. Let's say mobility challenged. People that have a hard time. So say you're in a wheelchair and it's a whole different world in a wheelchair and you're trying to get up a hill. Well, you can't, okay, so OSHA, you cannot make a handicap ramp where a ball rolling down that ramp would accelerate at greater than 0.5 meters per second, okay? Because it's not fair to somebody in a wheelchair that they have to try and go up that ramp. That's too steep. So ramps cannot have balls rolling down them at a speed, when the speed's up, when it speeds up faster than 0.5 meters per second. So now, so this is my V versus T. But what is my slope? What is the slope of this? The slope, what's the slope of the slope, in other words? This is the slope of X versus T. So what's the slope of the slope? Anybody want to hazard a guess? What do we call this? You've heard it before. The slope of this best fit line is, it measures how the velocity is changing over time.
Is it the weighted average?
It's not, okay, you know what? You bring that up. It's interesting you bring that up. It really isn't a weighted average because you know what we did? We took every one of these velocities are the same weight. They're all 1 second long. You know what I'm saying? So I could have, because it's linear, I could have just taken these numbers, added them up, and divided by 7 or whatever, and I would have got the same answer, to be honest with you, because it's not a weighted average. It's just a simple average, turns out. But the slope of V versus T is called drum roll please, it's called acceleration. The slope is acceleration. Acceleration, students are always, people in general, not just students, adults too, mix up acceleration with velocity. They're not the same thing. Acceleration is how the velocity is changing. So acceleration, so velocity is the slope of this function. That's this. Acceleration is the slope of this function, right? As we go to the graph below on a trio, it's always, I didn't write this in class, it's always, this is a virtual special, it's always called slope. As I go down to the graph below is always called slope. That's why it's critical that you make these one below the other. The next graph down below it is the slope. Okay. So now we got to find the acceleration. We're almost done here, but we got to find the acceleration. Remember I said the acceleration cannot be greater than 0.5 meters per second, or you violated OSHA standards here. So let's look and see what the slope is. Well, it's the constant slope. So let me take a simple number. If I go over 5 seconds, when I go up, I will cross 1.3, 1.2. It's all the same. So I'm trying to find an easy one where it crosses the grid. Okay.
3.5 and 0.9.
0.9 and 3.5. Okay, let's do that. So the slope then is, the slope is rise, which is 0.9 for this slope here. The slope of the slope. White, cut out some space here. Okay. So this slope, I'm trying to make it nice. So this slope, make it purple. Okay. So this slope is equal to 0.9, is my rise, 0.9 meters per second over, we said 3.5. 3.5 seconds. Okay, what's that? I don't know, calculator. What do you got?
0.26.
So this slope equals 0.26. And the units are meters per second per second. Now in this graph below, we're going to plot that. But you notice the slope doesn't change. So I call this, I don't know, I'll call this 0.1, 0.2, 0.3, and this is 0.26. So it's just a flat line all the way across. Doesn't change. In other words, the acceleration didn't change. Well, of course it didn't change. Gravity didn't change. That if you remember the video I showed you, that's a pretty good job of doing the ramp out there. And we meet OSHA standards. You cannot be above 0.5. So we're well within tolerance of building a handicap ramp. That wasn't really a handicap ramp. Okay. So voila, we have just completed our first trio. This whole thing, slow there. Okay, this whole thing is called a trio. Uh-oh, it's actually an orange trio. Shouldn't have been. It's an orange trio. Orange trio. Our first one. Now we're going to deal with trios for a while. And out of the orange trio, the next thing we're going to do tomorrow is we'll do this again. This time, that's kind of a homework thing, but I'll give them time in class and I'll let you do it. Just so you can do it all on your own. Do the whole thing on your own. And then we'll play with that a little bit. And then we'll start to derive actually orange equations. So you can derive a whole set of equations off this, which this is probably, of your motion you do in a day, and if you're sedentary, it's mostly first order, zero order, right? You're sitting in your chair. But if you're moving around, it's mostly consisting of first order and second order. First orders are duets, those are red duets. Second order is orange trios, and they're the orange equations. And if you include zero order, first order, and second order, you're gonna get in about 90% of your motion in a day. And you'll be able to after a while, physics gets into your skin and into your head, and you start thinking about it all the time. You're always thinking, okay, that's a second order. And third order, then I had Logan in class come up and push me in the back. Like I didn't notice, I mean, I did it on purpose, but so I didn't know it's coming. Well, that's third order. When you get shoved in the back, or if you trip and fall, or you slam into a wall, or you're in a car and you punch you slam on the brakes, it causes your body to jerk. And that's called a jerk, by the way. And that's third order motion. So you don't get a lot of third order motion in a day unless you're a herky jerky kind of person. If you're playing football, I suppose you do. But normally you don't get. Now, fourth order, if the K value is high enough, you're probably going to the hospital. You got hit hard, or you got banged. You're sitting at a stoplight, and a car comes creaming in behind you, and just plowed into your back. That's fourth order. That's whiplash. Okay. Anywho, most of motion is just zero, first, and second order. Okay, and this is second order stuff. So tomorrow we'll play with it a little bit more, and then maybe we'll start. No, it's Friday. I'll probably throw a little Galileo in there, and then we do Flashback Friday in class. That takes our last 7 minutes of class. All right. Any questions on this stuff? Your homework was due last night. You probably turned it in. If not, turn it today. You only lose a point or two. And that's 2.5. I know I have a lot of stuff. I have so many papers, and I've graded all the packets. Those I will put this weekend. I'll put those in the box, the handbags box, so you can come by and get those. You don't have to. I mean, you don't have to have your packets, but I'll put those there. You'll see the grades. You probably already have. I've graded all your stuff, and then I have to grade 2.1 and 2.5. I know I got those two grades, so we still got points out there. Okay. All right, we finished 9 minutes early. Any questions? Let me turn this off. Okay. Well, you've been a wonderful audience. I wish there was more of you. I mean, there's 25 virtual kids. Now, there's about 3 that I never see, but I do hear from about 22 of you. I'm guessing the other ones are looking at screenshots and somehow figuring it all out. I don't know. They don't really go to Facebook much either. So, maybe they're watching the recording. I do get quite a few. I got 50 hits on some of these videos. So I'm sure it's you guys watching. All right. Well, in that case, have a good Thursday, everybody. And we'll see. I won't see you tomorrow. Friday's my day. I'm gonna ride my bike. But I will put a recorded session, a wrap-up video that'll be available by Saturday early afternoon sometime. Okay? So I guess I won't see you live till Monday. All right, have a good one. Bye-bye.